Hey guys, welcome to the vibration analysis course. Week one, we're going to start off with a little video presentation here. It's not a lot of visuals, just going to just touch off on just the introduction. What is vibration analysis? What is vibration? What are some of the basic strategies that it's used in? And then from there, we're going to jump into some of the kind of more finer points in later weeks. So yeah, the first one is just the introduction. So I'll start with putting this to you guys. How many times have you been at work and you've put your hand on a machine to see if it was running right? With experience, you've developed a feel of what's normal and what's abnormal in terms of machinery vibration. So even the most inexperienced driver that's driving a car maybe knows that something is wrong when the steering wheel vibrates or the engine shakes. So, in other words, it's natural to associate the condition of a machine with its level of vibration. Of course, it's natural for machines to vibrate. Even machines in the best of operating conditions have some vibration because of small minor defects. Therefore, each machine will have a level of vibration which may be regarded as normal or inherent, is the word that we use to describe that. So it has an inherent vibration. However, when machinery vibration increases or becomes excessive, some mechanical trouble is usually the reason. Vibration doesn't increase or become excessive for no reason at all. Something causes it, whether it's imbalance or misalignment, maybe worn gears or bearings or looseness, broken bolts, on and on. There's lots of different types of conditions that can cause vibration. We will talk about those through the scope of this course. Since not everyone has the long-term experience needed to judge a machine's condition based on how it feels, various instruments have been developed over the years to measure the actual level or amount of vibration. In addition to that, human perception of touch and feel is somewhat limited, and there are many common problems such as the early stages of bearings and gear failure that are generally out of the range of human perception. So I can't put my hand on a machine and feel a bearing at the very beginning, early stages start to deteriorate. I can maybe detect it at the end of that deterioration, but I can't always detect it at the beginning of the deterioration. So modern instrumentation for measuring vibration on rotating and reciprocating machinery not only minimizes the need for extensive experience, but it makes it possible to detect developing problems which are outside the range of human senses of touch and hearing. So further to that, human perception differs from individual to individual. What one person may consider as bad, another person may consider as normal. So attempting to trend the changes in machinery condition using human perception is nearly impossible, since it's nearly impossible to put a documented number on how something feels. So if I go through and I say I don't like the way that this bearing is working, and then somebody else comes along and puts their hand on it and says it feels fine to me. You need to be able to measure and quantify and add a value to that vibration, so that even if we maybe disagree on what is okay and what is not okay, over time we can trend that it is getting worse, or we can apply some kind of quantitative number to it. I didn't change the slide, so that was vibration as an indicator of machinery condition. Let's talk about what is vibration. So vibration can be defined simply as a cyclic or oscillating motion of a machine or a machine component from its position of rest. And you're going to see this over and over again in our book as we start going through this course. Is if I go ahead and draw an object, and this object is attached vertically to a spring, and then it's attached to something it's hanging off of. Okay. Now, vibration really is if there's no actual force being applied to this weight here that's mounted on the spring, it's going to stay stationary. Okay. And it's not going to move. That would have there'd be no vibration in it. But if I come along and I apply a force on this vertically down, like I come in with my hand and I swat at that spring, what's going to happen is the spring is going to come down and it's going to stretch this spring, and then it's going to come back up. Okay, it's going to come back up. And so what you're going to see is if we put it on a timeline, you see that the spring is going to go down, and then it kind of comes along, and then it springs back up, and then it comes down. And depending on how much force is applied, if we hit it really hard, it's going to go really high, and if we don't hit it, and then it springs back down really far, and on and on and on and on. This position right here would be our position of rest. So when we go back to our definition, that vibration can be defined as a cyclic or oscillating motion. This is what that cyclic motion looks like when we trend it on a graph. Okay. And it's the difference between, if this is our rest position and it moves upwards, that's just the amplitude or how far it's vibrating. So the more force and the more the harder that the weight is struck, the more displacement, the more vibration is actually going to happen, the longer it's going to spring for. And in this example, we're saying that, like, oh, I'm just one time kind of swatting that weight with my hand to spring it and displace it from its position of rest. But in machinery, you have a machine tied up to a electric motor or a turbine or an internal combustion engine like a diesel engine or something. So there's a constant rotational or reciprocating motion that's taking place where you're constantly putting in the input. So instead of me swatting it with my hand just once, it's like I'm swatting it over and over and over and over and over again, right? So each one of those rotations is displacing this weight from its position of rest, and that essentially is what vibration is. So now we know what it. So I'll give you another kind of example of it. Is that if you have an electric motor that has a rotating shaft, the electric motor is not going to rotate exactly perfectly around the center, and there's going to be some slight kind of variance or change in that electric motor as it's running, right? And so when the bearings and the frame and the base and everything that's there, maybe it's just the vibration of machinery from something that's not like an outside environmental source of vibration. The machine on a microscopic level is actually flexing, like a plastic flexing, okay, and like a drum almost, okay, and that's happening at a very high frequency, and it's shaking, and that's essentially what the vibration is. So all machines are going to have some vibration. You can't eliminate all of it. So the next thing I want to look at is what causes it. Okay, so I gave a couple examples, but forces generated within the machine cause vibration. These forces may be ones that change in direction with time, such as force generated by a rotating imbalance. So we're going to cover balance in balance. We're taking a whole course in balancing. We'll cover it through that in that section. Okay. We're going to talk the change in amplitude or intensity with time, such as in an unbalanced magnetic forces generated in an induction motor due to unequal air gap between the motor armature and the stator. So if the electric motor isn't wired or positioned properly, or if it's been rewound incorrectly, we're going to be increasing the amount of power transferred through it unequally over time. So that's a possibility. It can be result in friction between rotating and stationary machine components, and it's much the same way that friction from a rosin bow causes a violin string to vibrate, right? So sometimes you can just have machine parts that are just rubbing against each other. That can cause vibration. It can cause impacts. The forces can cause impacts such as gear tooth contacts, or the impacts generated in the rolling elements of a bearing passes over flaws in a bearing race. So you don't have that nice smooth oil film that you're sliding across. Instead, there's a sharp edge or something where the parts actually hit. Or it can cause randomly generated forces such as flow turbulence, like in fluid handling devices such as fans, blowers, and pumps. So like the fan blades spinning inside of a duct can cause vibration. Some of the most common machinery problems that cause vibration include misalignment of couplings, bearings, and gears. That's number one. Unbalance of rotating components, looseness, Deterioration of ball rolling elements or rolling elements in bearings, gear wear, rubbing, um, aerodynamic or hydraulic problems in fans, electrical problems, resonance, and eccentricity of rotating components such as V-belts or gears, that kind of thing. Okay, so those are all some of the causes of vibration and things that we're going to detect. So we're going to get a little bit more technical here. We talked about what vibration was and what are some of the things that cause vibration in a machine. But the question might be why do we worry about machine vibration? We obviously, once a machine is started and brought into service, it will not run indefinitely. In time, the machine will fail due to wear and ultimate failure of one or more of the critical components. So, and the most common component failure leading to total machine failure is that of the machine bearings, since it is through the bearings that all the machine forces are transmitted. Of course, the next question is how long will the bearings last? And although an exact answer to this question is impossible, manufacturers of rolling element bearings attempt to estimate bearing life using this calculation that you see on the screen. So what we have here is L is representative of the life of the bearing. Okay, and then we have a constant here of 16,666. Okay, the RPM is rotations per minute. So for most electric motors, it's 1800. The rate is the rated load capacity of the bearings. So this is the rated capacity. So if a bearing is actually rated to withstand a certain amount of like radial load, so not axial in line with the shaft, but radial from the axis outwards, divided by the actual load. Okay, so then we have the actual. So this is the rate, and then that's divided by the actual load here. Okay, and then you take that number and you cube it. So this is cubed. So that this number in brackets times itself, so times itself 3 times. Okay, so according to this calculation, to estimate bearing life, doubling the rotating speed from say 1800 to 3600 would cut the bearing life in half. Right? If we take this number here, this RPM number, and we double it, overall the whole equation and life is going to come back as 1/2. However, by cutting the load on the bearing by 1/2 would increase the service life by 8 times. Okay, so if we take this load, that the actual load that and we reduce this one by 1/2, it's going to actually double or cube the result of reducing that load. So for example, if the load weight was like a number of 2, okay, just a unit 2, 2 times 2 is 4 times 2 is 8, right? So we can actually increase the bearing life by 4 times, okay? So of course this estimate of bearing life does not take into consideration other factors such as inadequate lubrication, lubricant contamination, damage to improper storage, installation techniques if you haven't done a good job of setting it up. So these are all things that this is at the core of why we're trying to reduce vibration. If we reduce vibration, what we're effectively doing, the RPM is something that we're not going to be able to change, but we can change this load right here. And if we cut that in half, if we cut that in half, then that translates into an 8 times length of lifetime of our bearing. So it's worthwhile to reduce the load, and that's what vibration is if we can balance things or we can fix it to not have that load on it, we can get a lot more life out of our equipment. So anyways, from this calculation, it can be seen that bearing load, including dynamic load and from vibratory sources such as imbalance and misalignment, and these are all things we're going to go over and we're going to talk about, it has a significant effect on bearing life and ultimately machine life. Further, the amount of vibration exhibited by a machine is directly proportional to the amount of force generated. In other words, if the imbalance force is doubled, the resulting vibration amplitude will also double. Or if the imbalance force is cut in half, the imbalance generated vibration will be cut in half also. Therefore, the answer to the question is why worry about machine's vibration is very simple. Increased dynamic forces reduce machine life. Amplitudes of machinery vibration are directly proportional to the amount of dynamic forces generated. If you double the force, you double the vibration. Logically then, you lower the amount of generated dynamic forces, the lower the level of machinery vibration and the longer the machine will perform before failure. So to put that all simply, so that's the logic of the whole thing, but putting it simply, low levels of vibration indicate low vibratory forces, which in turn result in improved machine life. So if we can reduce the vibration, we can prolong the length of the life of our machine. Of course, there's other reasons to strive for low levels of machinery vibration besides increasing time between failures. In the case of precision machine tools, maintaining low levels of vibration is necessary in order to manufacture quality parts from a dimensional tolerance and surface finish quality standpoint. Like, so if we have a surface grinder or something and we want to, excuse me, and we want to, grind something to a very fine finish, it's important to keep that down. And then like for example, like in a hospital or in some area where you're looking at ventilation systems or something like that, you want to have low vibration because of heating, ventilation, and so it's not annoying and just to keep the sound down. So with a few exceptions, when the condition of a machine deteriorates, one of two things will generally happen. One, the dynamic forces generated by the machine will increase in intensity, causing an increase in machine vibration, where corrosion or buildup of deposits on the rotor may increase unbalanced forces. Settling in the foundation may increase misalignment or cause distortion, piping strains, etc., etc. Okay, so the dynamic forces are generated, and the physical integrity of the machine will be reduced, causing an increase in machine vibration. So loosening or stretching of mounting bolts, a broken weld, a crack in the foundation, deterioration from the grouting, increased bearing clearance through wear of the rotor, loose on the shaft, would result in reduced stiffness to control even normal dynamic forces. So it should be obvious that an increase in machine vibration is a positive indicator of developing problems. So in addition, each mechanical or operational problem generates vibration in its own unique way. So as a result, it is also possible to identify the specific nature of the problem by simply measuring and noting its vibration characteristics. The technique of identifying specific defects and problems is presented in this vibration analysis course. Okay, not quite in this section, but in a later section. Okay, so we can reduce vibration, detect it and reduce vibration to prolong life. Okay, we can use vibration to do things like machine tools for creating accuracy of parts. We can keep things quiet. But really what we're going to be doing with our vibration analysis here is we can actually measure the vibration to detect what pieces and parts in the machine are breaking down or becoming worn out, to whether it's from dynamic forces of wear or deposits, or if it's a lack of physical integrity, such as the deterioration of the machine. Okay, so those are the things that we're going to do, and that's what that's what this course is all about, and what we're going to be able to do. So that brings us to the last part here, and we're going to talk about a comparison of maintenance philosophies. Okay, so in general, there are three ways to maintain machinery. There's your breakdown maintenance, there is scheduled or preventive maintenance, and then there is a predictive maintenance. Okay, so I'll start with breakdown maintenance first. So breakdown maintenance is essentially no maintenance at all. The machine is simply allowed to run until complete failure, inefficiency, or product spoilage forces a shutdown. Although many machines are maintained this way, breakdown maintenance has several disadvantages. First, failures can be most untimely, and there's little one can do beforehand to anticipate the tools, personnel, the replacement parts that will be needed to return the machine to service. Secondly, machines allowed to run to failure generally require more extensive repair than would have been necessary if the problem had been detected and corrected early. So some failures can be catastrophic, requiring total replacement of the machine. It's estimated that on average it costs approximately 3 times more to repair or replace a machine that has been allowed to run to total failure compared to the cost to repair a machine before failure. So catastrophic machine failure can also pose a safety problem for plant personnel, and the added cost of lost production while the machine is out of service can be staggering. So some of the plant equipment and machinery that it's valued in costs per hour. How much is downtime costing you? Okay, so there's a few things there. First, you don't know when it's going to break down, so you're not prepared and you're not ready for it. So even if it does break, it's not like you're standing there at the finish line ready to they fire the gun and off you go. It's like, okay, something is broken. What is broken? What is the extent of the damage? How many people do we need here? What tools do we need to get in here? And then you have to put that all together and then do it in a unplanned method where certain pieces of equipment can be critical and break down and the whole place is down. Okay, that's the one part of it. The other part of it is much more expensive. So the example, this is my first car was a Hyundai Pony, and I didn't change the timing chain in it. So a simple job to change the timing chain, which would have been about $500, the timing chain blew up. I lost the whole engine in my car because of a timing chain, right? So if I had just done that maintenance on it instead of running the thing to failure until it blew up, it would have been a very easy economical fix to have done, whereas I lost the whole thing. The final part of that is a catastrophic machine failure can also cause safety issues for plant personnel. The added cost of that production being down. So, it's just not the best way to do it. But in some cases, that it is a viable method for maintaining. The next is scheduled or preventative maintenance. So compared to breakdown maintenance, a program of periodic disassembly, inspection, and replacement of worn parts has a distinct advantage of lessening the frequency of breakdown repairs and also permits scheduled shutdown. Under this type of program, each critical machine is shut down after a specified period of operation and partially or completely dismantled for a thorough inspection and replacement of worn parts, if any. This approach of machinery maintenance too has its disadvantages. First, periodically dismantle every critical piece of equipment in the plant can be expensive and time consuming. Second, the interval between periodic inspections is difficult to predict. And if the program is so successful that no machinery failures occur, it may be that the interval is too short and money and production is being wasted. If the interval is too long, costly failures may still occur. So it's really tough to kind of time this one. And the type of maintenance that I would kind of associate this to would be like your car. Again, using the car example, you change your oil every so many kilometers. You change you do a transmission flush every so many kilometers. So you're taking a frequency or a time frame, and then you're saying whether it's broken down or not. Those are the times that I'm going to be doing that maintenance on it. The last type of maintenance is predictive maintenance. So predictive maintenance involves the trending and analysis of machinery performance parameters to detect and identify developing problems before failure and extensive damage can occur. So online detection and diagnosis of problems is obviously the most desirable way to maintain machinery. If problems can be detected early, then defects are minor and do not affect performance. And if the nature of the problem can be identified while the machine runs, shutdowns for repairs can be scheduled for a convenient time. You could also work schedule together with the requirements for personnel, tools, and replacement parts and get everything prepared before you're shutting down to fix it. You can avoid extensive damage and enforced failure, so the costs associated with that. Your repair time can be kept to a minimum because you're not having to go through and fix the whole thing from the ground up. And costly trial and error approaches to solve problems can be avoided since your analysis identifies the exact nature of the problem, if it's an inboard, outboard bearing, that kind of thing. The machines in good operating condition can continue to run as long as no problems develop. Time and money are not wasted dismantling machines and doing maintenance doing maintenance on equipment that's not needed. Okay, more uptime. That's a buzzword, uptime. Those are all the things that vibration analysis can do for you. You can go in and you can measure the vibration and you can detect problems, figure out a baseline of vibration, and then you can trend the variance. You can trend how much it changes from that baseline and expands up to the point where you have an alarm like, okay, this thing is going to break down, we need to get it fixed tomorrow or next week. And then you can get the people lined up and the tools lined up to go ahead and do that job before it has a catastrophic failure. And you also know exactly what's going wrong with it. So if it's an inboard bearing, or if it's a gear, or a gear mesh, or whatever it is, you can kind of get things lined up and know exactly what you're walking into. That's what vibration analysis and predictive maintenance does for you. It doesn't always necessarily have to be through predictive maintenance. Vibration is a predictive maintenance tool, but there's a lot of other types of things, that parameters and things that we can look at. We can look at do lube oil analysis. We can do ultrasonic thickness testing. We can check the motor current and you can see if we're losing efficiency in the motor, or it's drawing higher amperage or lower amperage, and what that means. We can do infrared thermography, which is like your heat map, like looking at things like red is hot, blue is cold, kind of like pictures. Take pictures of things and see, because where generates heat, so we can kind of trend pictures, and we can actually look at the change in temperature based on infrared pictures. And we can also measure bearing temperature. So in addition, machinery performance characteristics such as flow rates, pressures can also be monitored. In case of machine tools, the inability to produce quality product in terms of surface finish can be an indication of problems. So there's all these techniques that have value and merit. However, the one characteristic that is common to practically all of these machines is vibration, and that's really at the heart of what we are going to cover here. Is vibration, measuring vibration, using that ability to measure vibration, and how to use that within a predictive maintenance program. Because ultimately the predictive maintenance program, although it takes a lot of time and effort to get set up and get moving in that direction, it is far and away the most advantageous maintenance program, because of all the reasons that I just talked about. The planning, the preparation, the costs, the downtime of the machinery, all of those things all play into that. So that is your introduction to machinery, machine vibration, and maintenance strategies. There is going to be an assignment in the week 1 section of the course where you can do a little bit of like a reflection or a case study of explaining what kind of maintenance strategies you have worked under or within. And next week we're going to dive into some of the steps and what goes into a vibration predictive maintenance program. What are some of the things that we're going to do? The detection, the analysis, the correction, and some of that information. So that's all. See you next week.